This is a video for AQA Further Pure Mathematics. Vectors, section 3.1, equation of a plane in parametric form.
Well, previously we've seen that there's more than one way of writing the equation of a line in 3 dimensions, and the same is true for an equation of a plane. So in this video we're going to be looking at one way of doing that, which is parametric form. You'll remember that for a line the parametric form was r is equal to a plus lambda d, where a was the position vector of a known point on the line, d a vector in the direction of the line, and lambda some scalar multiple of that. So r equals a plus lambda d gave us the parametric equation of a line. Now this is similar when we come on to a plane, and it's a very convenient form when you know direction vectors that lie in the plane, or you can calculate those direction vectors from known points in the plane. So before we go on to that, just show you some examples of this on a GeoGebra file. Well, here we can see a plane where we've got a known point A, and the position vector of A is given by little a, and then two vectors in the plane B and C, which are defined by 2 points P and Q, so that the vectors are from A to P and from A to Q. You can see then, if I tilt that those two vectors definitely lie in the plane, and A is a point on the plane. If I move P, then if I keep it in the plane, you'll see that the plane doesn't change. If I move it, then the plane is starting to move. And again, as long as A is some point on the plane, then it's not going to change, but I can then alter the position of A to give different planes. But in all cases we've got the plane defined by a known point A and then two vectors B and C, which we can calculate from other known points. So here's a general situation that we have then. We've got that the position vector of R, a general point on the plane, we can find from the known point A, and then multiples of the direction vectors B and C. So the multiples will be different, so we tend to use lambda and mu for those multiples. So we've got A plus lambda B plus mu C, giving us our general point R. So we've got a known point, a multiple of a direction vector, and another multiple of a different direction vector which is non-parallel. Remember that the direction vectors B, for example, might be equal to a vector from A to P, so that if this is point P here, and that will be found by the position vector of P minus the position vector of A. So we can imagine going from P back to the origin and then to A. So minus P plus A, or P minus A for the direction vector. Well, now let's look at an example of the sort of question you may be asked to do. Here we've got a plane containing 3 points, P, Q and T, with their coordinates. And we're asked to find the vector equation of the plane containing these 3 points. So we're going to need two direction vectors. We can get those by looking at the vectors from P to Q, which will be vector for Q, which is 0, 3, minus 1, minus the vector for P, 1, 2, 0. So that gives us -1, 1, -1. for one of the directions. A second direction vector be from P to T. That's going to be equal to the position vector of T, -1, 1, 3, minus the vector for P, 1, 2, 0, and that's equal to -2, -1, 3. So those are our two direction vectors. We can then write that the equation of the plane R is the position vector of P. So we've got the position vector of P plus lambda times one of the directions PQ plus mu times the other direction PT. So we end up then with R is equal to position of P 1, 2, 0 plus lambda times one of the directions, -1, 1, -1 plus mu times the other direction, -2, -1, 3. And that's our equation of this plane in parametric form.
Well, that concludes this video. In the next one we'll be looking at the equation of plane in other forms.